let's get started. So we'll have, so the journal club sign up. Well, first of all, do you guys know there's a class group me, right? Raise your hand if you didn't know there's a group or know what a group me is. So basically for the class to basically talk to each other, in previous years I used Piazza, but no one likes that. So I just use what the students use. So basically if you go to the syllabus at the very top, there's a link now that says class group me, and you click that and there's a thing on your phone. But basically this is how I need to reschedule office hours, which I do, or if there's some kind of announcement, or if someone has a question, a general question on the homework, I try to answer it with the class group me. So please add yourself to it. The distance learning people, I think you'll stay with the current class, but I think we could have a whole different group me. But feel free to, please add it before you forget. This class is recorded every lecture. It's on Canvas Media Gallery. I think it takes 24 hours for them to show up, but you can look at things there. Okay, so if you remember, let's see, the 60% homework and quizzes, we'll have our first homework due, not this week, but I think it's due next week, right? Let me see. It's due after the holiday. Yeah. So we're not going to have a class on Monday. So you should pretty much finishing the homework Monday and Wednesday, and you can ask any remaining questions on that Wednesday. But it'll be due on Friday, and we'll have the quiz as soon as we get back from the holiday. Remember, we got 10% Journal Club, which I consider a giveaway for the class. So make sure you sign up for the Journal Club so I can see your enthusiasm for having a giveaway points. But I don't see too much enthusiasm for the giveaway points. So on the Canvas, there's a Journal Club sign up. Just so you don't hear me droning on like week after week. For example, this Wednesday, Ethan Weeks, you're going to talk about microfluidics. And I think Ethan Weeks posted a group me. But maybe if anyone wants to join you. Okay.
It was open.
Okay.
That's why I sent the message if anyone.
Yeah. The Journal Club, since we have so many people in the class, it is also nice to try to work with each other, but also in a fair kind of way. Don't just add your name. So please just make sure you reach out to Ethan more than like 6 hours in advance and be like, hey, can I help with your presentation? And we'll do that at the end of class this Wednesday. But please start to sign up for the other weeks. If we run out of time, we can do it Monday. But we don't want to go into the final presentations, which is the end of the class. You can talk to the people next to you when we do the group work. You can even put a topic here, and then maybe someone can reach out to you on the group me. But I would start to claim your spaces. Like we have a to be determined here from Mr. Don. Okay. All right. So please sign up for the Journal Club. Yeah. And then if you start having ideas for the course talk, you can always send me an email or talk to me after class. That should be a fun part of the class. All right. So last time we were talking about, we were going through Cauchy's momentum equation, but I do want to make a correction before I forget. I think, what's your name? Yeah. Daniel. Okay, Daniel brought this up last time, and I think I just answered it off the cuff, but I was thinking about it. When you have basically this index notation, you can only evaluate it if you basically see the same index twice. That's the whole point of the index notation. So for example, this index notation cannot really be simplified too much more, because you can only go from I equals 1 to 3. There's no j summation here because j only appears once. So you can imagine this as an invisible summation over I. And then this one is going to look like this. Delta 1, 1, delta 1j plus delta 2, 2, delta 2j plus delta 3, 3, delta 3j, where I'm just summating over the i's. And that is just going to be delta 1j plus delta 2j plus delta 3j. So this doesn't actually get that much simpler. You can't solve for a number for this one. The first 3 problems on the homework, if you remember, they all have summation appearing twice for the i's and j's. And that's why you can actually come up with an expression, like a numerical expression for those. Okay. So contrast that with the homework. The homework for the first one, you have delta ij, where we did that by writing all 9 terms. Another one in the homework, epsilon ijk, epsilon kji, where I, j, and k both appear twice. So you can imagine you have 2 imaginary sums, epsilon I, j, k, a, I, a, k. The a and the k, sorry, the I and the k's appear twice. The j, so this is going to have some j component that's going to just stay left over, et cetera, et cetera. Okay. So this top term can't really be simplified. So last time we ended with doing this one index notation. I wonder if we should do that as a warm-up, because we're going to be using that fact. Yeah, I hear yes. All right, so let's do that as a warm-up. Now that you're all have a little more practice. I'm gonna get rid of this keyboard, and let's go to full screen. All right, so last time we were trying to prove the following: del dot rho u is equal to the sum of 3 terms. Okay. So let's do this as a warm-up. Show, and this is equal to u dot del rho. And remember, those are rho's, not p's. This equals to rho, not pressure. Plus rho u dot del u plus rho del dot u. All right. So I'll start with the left. So we're going to call this d differs by x, and then I'm going to write index notation for each of these terms. A scalar, start with I, u.
If it's the same variable, why does it have a different index?
UU is a tensor. Anytime you introduce a new instance of that variable, you have to use a new index, because it increases like the order of the thing. So let me just write that. New variable. Use new index.
I have a question.
Yeah.
Why did you do del xj and then uj again? Why don't you use j twice?
Let me. I think you can do it in a different way too. You can try to do it your way, and they should not come with the same answer. Let me see if I can find my notes and I'll redo it. All right. Okay. All right. Let me stop skipping steps, and let's do it. All right. So this is how I did it. All right. So if we were to be really without skipping steps, we would introduce a new variable, use new index. So I would start with dxl el dot rho uj ej ui ei. Okay. So you basically have this tensor on the right, which is the uj and ui's, and you have this derivative here. Right. All right. So now we got to bring, so the EL hits the first, the reason why that had a dxj was because this EL hits the first dot product here, right? So let's move. So then that's going to become dxj rho uj ui ei. Okay. All right. So the reason we get three terms is because this derivative hits on each of those three terms sequentially. So let's just do those separately. So first by the rho uj ui plus duj dxj ui plus rho uj dui dxj. All right, and these are all in the I direction. So there's equal signs. All right. Now, how do we show each of these are those following terms? Well, this one, you think about it, basically, this density got hit with a derivative and is in the same direction as this uj. So this term is going to be u dot del rho, right? Del rho is going to give you a vector, and if that's dotted with u, you're going to get the same j symbol, right? And that's multiplied by u, okay, because you have this I term. This one, uj and xj are all in the same direction, so you got rho. This is going to be a divergence of u, right? And that's not affected by the second u, so we have a u there. And this last one, uj has the same index as the derivative. Therefore, you have rho u dot del, because they're the same direction as the derivative of u. Okay, plus. Let's stop for a second. You can ask me some questions. See if that makes sense to you. I see some furrowed eyebrows. Yeah.
So, is it incorrect to kind of treat the ddx as like an operator and split it up? And is that where you get like in the third term where it's rho dot del u?
This term?
Yeah.
Yeah.
Or like in the second term.
Oh, this term?
Yeah,
Yeah.
like where you get a del u, where they're like, I guess when you say, when you do that versus like the divergence.
Why are these different?
Yeah. Why are those different?
So as exercise, while I'm answering this question, I suggest everyone translate these to vector notation, like if this is not clear to you. So for example, this one, del dot u means del and u are going to be in the same direction. So del dot u is going to be, if I just do that, ddxi ei dot, again, a new one, uj, ej, those are going to become, it's going to become duj, and the ei dot ej is going to be a Kronecker delta, and this is going to be duj dxj, right? So divergences keep it and basically have it look like this. And that's the key thing. It's because of this dot product, okay? And that makes the i's and j's like become friends, and then you have to stick with this. This is different because this j here is matching with the derivative down there, which means you're going to have something like this. So let's just translate this into words. So you got ui ei dot d dxj ej u l e l, right? So these two are interacting. So they become basically uj d dxj, and then you have u l e l, and that's what we have up there. So it's basically, the difference is like, it's what term they interact with first. I'm sorry if that's not very clear, but it's basically when I do it. So when I did this problem, what I would do is I would do this, and then I'd come up with the terms that I need, and I would go backwards, and then eventually you kind of start to get intuition for like what it's like. So if at your seats, if you want to each redo these, I think we'll still wait another minute for people to have questions before we move on. And if you missed last week's lecture, and 2 weeks, this is going to be like, you're like, am I in the right class? What is this? there's a handout called on index notation that's going to help you. But you're probably just going to have to like try to spend a few hours and talk to people. Do you want me to do it this left-hand term, or is this okay? You're good for this on the quiz, right?
Could you do the left-hand term as
I
well?
have a lot more work to do.
What?
Can you do the left-hand term as well?
Yeah. Well, here, why don't we do this as a class activity? Tell me what to write. What's your name again?
Elias.
Elias, tell me what to write here.
So.
And it shouldn't matter like what dummy notation we use.
Okay. Well, we can move the row around, right? Because it's just a constant.
This is del rho.
Or no.
No, because this is acting. So this is saying the velocity vector dotting with. So rho is like a scalar function, and we're taking the gradient of that, which is going to give us a vector, and this gives us a scalar. So we have to keep it there.
Okay. Well, then yeah, it'll be a u dot del rho.
Well, let's go index notation.
Okay,
What do I
yeah,
write
yeah,
first?
I mean, then like del rho.
Well, you want to do this term, right?
Or yeah, sorry. Oh, okay. Do you always start with the vector, or?
I usually go from left to right. Can anyone read out what I should write, just as practice?
UIEI.
Okay, UIEI, thanks. UIEI, yep, dot.
Del rho.
DXJ, because this is the underlined sign means the vector. So it's a new vector, and this, in fact, the vector is this. Sorry. So that's the gradient vector, and then now what? Rho, and then what about for this U? Yeah, sure, ULEL. So how do we do this? We went left to right, and I introduced a new letter for every vector. See those underlines? I introduced a new letter for every vector. And those letters are arbitrary, right? As long as I'm consistent with, like, basically this derivative better go with this vector, because that is the gradient symbol. Gradient, remember, gradient means dxi, ei, where I can be j or k or whatever. It depends on, like, what I start with first. Okay. All right, so
Always going to match.
this is the definition of gradient. No, it's gradient only if you have an operator. What do you call it when it's just by itself? Nabla? Nabla? Who's Nabla? What language is that?
We call that operator as Nabla.
Oh, okay. Nabla. Sounds like a boogeyman. Nabla's going to get you. All right, okay. So this. All right, so now next step, basically, the i's and j's match, right? Remember we had this rule that says e dot I dot e dot j with a Kronecker delta, which is basically saying that I'm going to keep one of them. And the one I'm going to keep is the one that basically has, I have a j down here, so I'm going to keep the j. So that means,
Change all the i's to j.
yeah, sorry, this is very sloppy. ui. Yeah, so it's going to be uj, dxj. That's it, right? And then I'm going to just copy down what I have up there, ulel, right? Right, and this just acts on rho. So we're going to uj, d rho, dxj. And then I'm going to have the other stuff, which is almost like independent, because I haven't even touched that part of the problem. Like this means that this is like just a vector, right? And this, sorry, my handwriting is not good. So this will be u dot del rho, and this is multiplied by u, and that's what I think that's what I try to find. Yeah. Equals. Is that better now? All right. Definitely, this is the last week before the quiz, so definitely come talk to me. If you're doing the homework, so this is my suggestions for this homework. Homework, I would do the exercises in the handout first. I think I wrote this last time. Don't do the homework unless you've done the exercises, because the homework, I would say, is somewhat harder. Then do the homework. Do homework one by one, and maybe check with your friends that you're getting the right answer, because they sort of get progressively harder. But once you know how to do this, it's not so bad. All right, so this was basically, and you're going to show, this is basically identity, that we basically have that is separated into these four terms. All right, so let's use that fact and go back to our notes. Do people want to do another board session in the class with the index notation? Do people want to spend time on the homework in class?
That would be nice.
Okay, all right, so we'll spend at least 20 minutes or so. All right. So last time, we were doing conservation of momentum. All right. So what we had is we were trying to figure out the momentum statement to get to Navier-Stokes. Okay. And we're going to try to go from, so what we stopped with last time, we had a volume integral, a surface integral, and two more, and then another volume integral and another surface integral. So this is a volume, and this is a surface. Where we introduce this notation this is a t. This is going to be, we're going to spend a good amount of time on trying to figure out how to write these surface forces. This is the stress vector. We're going to find some relationships to do with the stress vector to show us there's some symmetry for Newtonian fluids. All right, so all right, so let's see. The first step we did last time was we're going to move in, since the volume is fixed. The volume is not changing with time, so basically we can take the time derivative in. That'll be one step. And the second step here, the next part is we're trying to figure out what to do with this term, and that's where we use that identity that we just used. So divergence theorem tells us that if we know this amount that's fluxing through the surface, right, I can write that as that same amount that's being diverging in the volume. Remember, divergence theorem is perfectly general, and we just throw any function into it. And this function we're putting is this rho u. Okay. And well, we spent time with index notation, and honestly, I don't think there's really any way you can do this without index notation. We separate that into three terms, which we're going to be taking care of piecemeal. So this is from identity. We're going to write this. So that term, we're going to write that as the three terms. U dot del rho plus rho u dot del u plus rho del dot u. And they're all different. I mean, they basically, I mean, if you were to say them, they would be different. For example, this first term, you would say this like, this whole thing is a vector that's in the velocity, in the direction of the velocity, and the magnitude of that vector is given by how much the velocity has in parallel with basically the gradient of the density. The second term is basically has this u dot del operator that's acting on u, and that's scaled by the density in the front. And this last one has this continuum, like a conservation of mass term in the middle that tells you its magnitude, and it's also in the direction of u. So for example, this first vector and the last vector are both in direction of u's. This one, not so much. And so this will be dv over v. All right, so we put all this together. All right, I'm going to call this equation star from last time. First two terms of star, let's put it together. Rho du dt plus u. Oops. Plus u d rho dt plus u dot del rho plus rho u dot del u plus rho u del dot u. All right, I just rearranged it a little bit. All right. All right, this is over the volume. Let's combine terms. So rho dt plus u dot del u. Right, this is going to be our material derivative. And I'm going to put the remaining terms here. All right. Maybe from your notes from last time or some of the top of your head, can you label some of these things I put in parentheses? The first term, what do we call this? Yeah. So this is the material derivative applied to the velocity vector, right? That's just the definition of material derivative. All right. You might have to look in your notes from last time, but the right-hand side, what is that equal to? It's okay to spend a third minute going through. It might have been even 2 lectures ago. Yep.
Was it 0?
Yeah. That's what we derived. This was conservation of mass. So this is 0 by continuity. Let's realize it. Continuity. All right. So we proved that the other day. All right. So what do we have left over? Thus, we just have the following left. Rho. Oh, come on. The volume integral of the density times du dt across any body forces. And now we have our stress vector, S. Okay. So star became this because half the terms disappeared. All right, so the first fluid dynamicists saw this. They're like, hey, I'm trying to come up with a governing equation that's valid at a point. But the problem is, bless you, this stress vector is not exactly the form I want. But if I could make up a new idea, so this is what they did. They basically came up with this idea. So to make PDE, you basically made up this idea that basically T was equal to a normal vector, which gives you, because T is already a stress vector at the surface somewhere. It's defined everywhere along the surface. And so if we can define a vector everywhere along the surface, we can define this stress tensor. And the definition is that the stress vector is basically all the information in the stress vectors in the stress tensor. Now, in the homework, I think you started looking at tensors. Tensor, for example, that what I think Don was asking about, that u times u, ui times uj, that is a tensor because you've got 9 different components. You know, you got the u1, but also you got the u1, u3, etc. So let's talk about the stress tensor. What does it mean? All right. T is a second order tensor. Second order means that it's like a matrix as opposed to like a row column. First order would be like, you know, your typical vector. Second order tensor. And in this case, because we live in a 3-dimensional world, it's a 3 by 3 matrix. Okay. With 9 components. All right. Which will be there'll be functions of the pressure and velocity fields. All right. So some notation, e.g. T12. So there's 9 components, T11 all the way to T33, but T12 is a force per area acting in the E2 direction on a plane perpendicular to E1. Bless you. All right. Okay, so clearly there are 9 different components. And this idea was first developed by Cauchy. So this is Cauchy's big idea. All right, that we're going to put information in this T and n dot T. And his motivation for doing that is so they could use the divergence theorem, because divergence theorem tells us if you got normal things that are normal, you can apply them and make them into divergence. So, so by divergence theorem, we got T of n ds. I'm going to just use this definition, n dot t. My n's are s ds del dot t dv. This might be the first time, that's supposed to be a dot product. Oh, it's getting You probably have seen divergence theorem with vectors, but you haven't seen with tensors. But I think there's a proof in the handout that it works with, doesn't work with scalars because it doesn't make sense, but it works with vectors, it works with second order tensors, and we will encounter a third order tensor when we get to angular momentum. Okay. So let's see. So I need to relabel. This we're going to call box. So I relabeled that equation box, and then let's call it with the x through it. So x becomes rho du dt dv is equal to f dv plus del dot t dv v. So this is what we want because everything is a volume integral. Since v is arbitrary, integrand vanishes. We can basically look at the integrands. All right, this is Cauchy momentum equation. Because we derived it by looking at conservation of momentum. And I believe you have to do this for your first homework. For homework 2, when you're done with the index notation. And I would encourage you to start with the homework 2. Because these lectures basically deal with homework 2. Homework 2 says, in class we derived Cauchy's momentum equation by examining momentum to budget within a volume element. Rederive the equation by considering the force balance on a fluid deforming with a flow. Apply Reynolds Transport Theorem. Do not assume the fluid is incompressible. Okay, so you're going to redo this by not assuming for an arbitrary fluid. Okay, so for the homework, you're going to use Reynolds Transport Theorem. Oops. Which we won't prove. Reynolds Transport Theorem basically says you can move a material derivative inside the integral for a moving control volume, moving and deforming control volume. And this is true. For psi equals s, a scalar. All right. Or vector. So for the homework, you're going to need to use the following version. Homework 2, you need to use psi is equal to rho f. Okay. Which says that basically if I've got a body force per unit mass, dV, I can rewrite it like this. So you're gonna prove this. All right. This class starts at 9:30, so 45. What? The class ends at 10:30? 10:45. So we have 35 minutes.
And what did you say that double bar F represents?
Oh, this F vector?
Oh, I see. That's just a vector of
This is just,
okay.
just an arbitrary vector. Yeah.
Gotcha.
Yeah. Why don't we give a roadmap of what we're going to do a little bit next time? Okay, so this Cauchy momentum equation. This is not. It's general, but it's not very useful. We haven't specified if it's a Newtonian or non-Newtonian fluid. This is true for all kinds of fluids. But you notice there's no viscosity in there. Viscosity comes from behavior of the stress tensor. And to understand like where that comes from, you have to go conservation of angular momentum to basically get the viscosities and pressures out of that. So that's what we're going to do. We're going to do a little bit next time. But let's define. So next time we're going to be doing. So this is basically the end of Cauchy momentum equation. So now we have conservation of angular momentum. All right. So starting with using, let's make this a little bit bigger. Conservation of linear momentum. So Cauchy momentum equation. The goal of the reason why we're doing conservation of angular momentum is we're trying to express T in terms of velocities and pressures. All right. So the idea is we're going to use conservation of angular momentum on a moving deforming element and demonstrate that T has some special properties. The stress tensor is symmetric. And that helps things because if it's symmetric, how many components does it have? If it was originally 3 by 3. Yeah. Those along the diagonal and those top 3 from 9 to 6. All right. So here's the word statement of conservation of angular momentum. All right. So all right, so we have some coordinate axes here, and let's say our volume is it's just some position vector x away from the origin, and again there's fluids going through it. So we got V and S. translating that word statement into equations, the time derivative of the angular momentum. So angular momentum is going to take each element in our fluid volume crossed with its position. So take that linear momentum and cross it with the position. We're going to have two terms. Oops. Plus G D V V. And we also need to cross the surface forces. All right. So we're gonna call this part 1. We're gonna work on that next time. This is the torque from the body forces. G is if there's any kind of body couples for a unit mass. So G usually maybe only for like ferrofluids or something like that. And this is rare. And this torque is torque from surface forces. All right. So the only time you would have G is if you have a ferrofluid, for example. Possible for ferrofluids. Ferrofluids used to be a pretty big research area when I was in grad school. I think now they appear in brakes, but basically it's a suspension of fine magnetic particles in a fluid. And they can exert a torque if you apply magnetic torque. Particles in a fluid. Some brakes. Okay. So we got 25 minutes. I think we'll take it up here next time, where we're basically going to take these three terms and simplify them, and then get some ideas for how the stress tensor behaves. And that'll be pretty much the end of our Navier-Stokes. And we'll talk a little bit about non-Newtonian fluids. Okay. Now for the homework, maybe let's just go through from the beginning to the end. Where is my homework? I encourage you to work in groups for the homework, but when you write it up, you should really write it up without like copying it straight up, because on the quiz, it's going to be very, very evident if you're not doing it independently. So I encourage you to work with people, but basically when you write up, you should be able to rederive everything on your page. All right. Oh yeah, about this. I can post answers. We can go over the answers, but I'm grading you on the homework, and so I think I want to see how you do it.
Because the homework is due after the quiz.
It is after the quiz. Yeah, but I can go through. I'll give you answers for each one. I mean, most of this homework is proving that these are true. So, like these identities, you either. So I think we can do some in class. Let's do that. All right. So homework. What do people get for number 1I? Delta ij, delta ij. I think we did this in class, right? 3. All right. And you can shout out if you got something different, and we can go over it. All right. 2. Epsilon ijk times epsilon I kji. Epsilon kji. Do we need to do this together? Should we do it together? Yeah, let's do it. All right, this is a good application of that of this theorem. Not really theorem, but basically, all right. I think I wrote this on the top of the board last time. But basically, this is an identity. Epsilon ijk, epsilon klm is equal to the sum of these delta functions. Delta il, delta jm, minus delta im, delta JL. Okay. All right. So I get confused with the notation. Basically, I rewrite this as basically delta 1, 1, 2. Basically, I consider you have basically a first term and a second term, and this first number means the first term, and the second number means the second term. So this is from the ijk's, and this is from the klm's. So this is delta 1, 2, delta 2, 3. Minus delta 1, 3 times delta 2, 2. All right, so see if you can, at your seats, substitute that in and solve for this one. And if you haven't done that already, if you already done that, you can do the next term and the term after that. And if we have to extend the quiz, I think we could do it one time if people feel like totally stressed out and overwhelmed, but it will come. So it will not be extended indefinitely. So, and we have the whiteboards and stuff, so let's pass them. Do people like the whiteboards? Or not really? Does anyone want one of these? Okay. Raise your hand if you want a whiteboard, and I'll come over. Otherwise, they'll stay over here. All right, here's one. You can share. Does anyone, no one else wants them? Anyone want them here? Yeah, one? I couldn't tell if that was a yes or no, but you were looking like this. Okay. Here you go. There's 2 more. Anyone else want them? Yeah, one here. Last one. All right, I'll leave here. And I've got the markers. This part of the class is not graded, so definitely try to work it out. Raise your hand if you haven't done this one yet. Has everyone done this one already? Yeah? All right, should we just skip it? Who wants to go over this? All right, okay. So try to use this identity. So actually go term by term and write the identity for that product. So you see, the thing with this identity, the thing that's required is for you to apply this, they both have to have the same, the last of the permutation matrix for this one has to have the beginning of the permutation matrix of that one, right? Permutation matrix, it's either +1 or -1 depending on the permutation symbols. These are 27 values, and it's either +1 or -1 depending on the order of the stuff in there. All right, so for background, basically, where does it come from? It comes from the fact, we went over this last time, stay across each epsilon ijk, ek. And that's what this means, okay? It has several different properties. All right. All right, so how do we apply this? Do you want me to let you do it on your own, or do you want me to talk about it? Talk about it? Okay. All right, so can we apply this or not? Is it that has the right format? And it does, because you can tell, because there's two k's here. Those are overlapping, and the other index, I and j and I, they don't have any k's, so that's fine. All right, so now we basically just have to substitute this in. All right, so let's go term by term. This first delta is basically the first. You got this first permutation matrix. It's the first one, and here it's the second one, IL. So we take the first one and the second one. So the first one is going to be delta. The first one is going to be I. The second one in this case is going to be j, right? Okay. Then the second one is the second term of the first one and the third term of the last one. So second term of the first one is going to be j. Third term of the last one is going to be I, right? And then the etc. So this one we got the first and the third. So we got I, and then we have second, j. All right. So see if you can work on this one at your seats. I haven't done it yet. Okay, so this is basically, imagine you've got some imaginary summation symbols here, right? Oh, why is this getting messed up? I and j, right? So this one we solved last time. This was 3 minus, and basically, imagine to write all these are basically independent. So this is 3 times 3. So this should be -6, right? Do people need to work it out more carefully?
So
Yeah.
that first one, you can kind of take a shortcut and just say Sij times Sji is just Sii. Because you kind of got a substitution delta against the substitution delta.
Yeah. So this is what Don was saying. Well, delta ji is equal to delta ij, and then delta ij. We did that before. We did that up there. And this is only true when I equals j. And you can imagine this is 9 terms. This is what we did last time. Delta 1, 1, delta 1, 1, delta. We did this delta 2, 2, delta 2, 2, delta 3, 3, delta 3, 3. So the only ones that remained were the diagonal. That's what we did last time. And here it's basically, this delta I is summed by itself and multiplied by delta jj summed by itself. So delta ii's are just basically delta 1, 1 plus delta 2, 2 plus delta 3, 3. That's its own summation, so that's going to be 3, and then same for the other one. So we're going to do each of those independently. This is like you're doing each of these separately, right? Questions? Everyone totally gets it? Okay. All right, number 3 on the homework. 3, epsilon I j k a I a k. All right. So you can rewrite that as negative epsilon I k j by just switching the notation. That's what there are 2 properties: the cyclic property and the what do they call it? The interchange property. So this is the interchange property. I a k. Okay. All right. So this one is A cross A in the j direction. In the j direction. but it's also negative of itself, right? A cross A in the jth show. So basically the only way it can be anything, it has to be 0. And A cross A is also 0 too. Actually, we'll just leave it like this. I'm getting confused with the next one. So this is a vector cross itself. Vector cross itself has no area. Remember, the physical analogy for a cross product is you looked at the area between the two vectors. Cross itself has no area. All right. For epsilon I, j, k. All right. So here, we can also use the interchange property. Epsilon j I k d squared phi. So this will be negative dxi dxj, right? Where I've just switched, basically I sent I to j. I did a, how do we call that? Switch the dummy variables. Change dummy variables. Right. But these are basically going to be the same thing. So those are going to have to be 0 too. Oops. That's from above. But then we can switch it again. Change. So this is from the interchange property. Interchange property. Sorry. Yeah. Interchange property. Of epsilon. All right, interchange property, I'm just switching these two. But you could also do it by changing the dummy variables. Epsilon I j I k d squared phi dx I dxj. Right. And so if it's equal to itself negative, then it has to be 0. Only, and this is from I, j substitution, change variables. Only, so basically it's a negative of only number that's equal to negative of itself is 0. So the top one's interchange property, the bottom one's change variables. And you notice one of them you have the negative sign, and the other one you don't, but they're basically the same thing, right? Because the order of differentiation doesn't matter. We just say differentiated is commutative. Okay. Questions on that? Is that okay? All right, number 2.
Actually, can I ask a question on that?
Yeah,
Okay, so if the variables for the derivative needed y and x, give us something to go with.
Your microphone, maybe go a little closer to the microphone and talk a little slower. All I heard was that I heard like a lot of blank spots. Say it one more time.
Oh, I'm sorry. My connection's bad.
Oh. Maybe I should have written it like this. Is that better? I can go from the first term to the second term, and the first term to the third term.
Okay, right. So then, why is the second and the third term would have different?
The second and third term equal because they were both derived from the same first term, right? Why is the second and third term equal? Because it's just switching the order of the derivatives. This derivative is commutative, so I can switch these. Switch those orders, right? Derivative of phi with respect to I then j is the same thing as respect to phi with respect to j then I, right? All right, let me just write this. To be dwell squared phi. So what does commutative mean? That means dxi dxj is equal to d squared phi dxj dxi. You know, we did a lot of the other problems where the order did matter, but when you're taking a scalar function like that and you're taking the derivative, it doesn't matter the order, right? Yeah?
So should the third term also have a negative sign?
No. If it were a negative sign, then it would be what I have up here. I derived this third term from going from the first term and doing the substitution. I said for every I, I'm going to switch it with a j. And that's what I did here. So for the I term, I made it into a j. And for the j term, I made it into I. Yeah. So that's why I made the correction. I'm like, this one becomes here, and this one also becomes here. But these first and third term are the same, except with this negative sign. So the only way it can be anything is if it's 0. All right, and this is...
So the epsilon, I thought that wasn't commutative.
It's not commutative. The derivative is commutative. This d squared, the derivative with respect to the xi is commutative. Epsilon's just like it's a number, +1 or -1.
But the order,
Change the dummy variable, then wouldn't that be the cyclic property? So that would pick up a negative.
This is the interchange property. That's why this negative comes out, because of this interchange property of epsilon.
Right. So the other one would be the interchange property too.
No. I just use, the whole idea is you got to use two separate facts. The first one you use the interchange property, the other one you use the change of variable. You got to do two different ways. If you do interchange again, you could also do it I think what you're saying is valid too. You could do interchange twice, and then you're going to get where you are. So I think what you say is fine. It's just another way to think about it. All right. Is there a question? Sorry, keep on missing.
Why is the third term
not negative?
Because, like, according to the first epsilon, like, it's ijk in the very first term, and then in the third one, we're...
Did you mean to write ijk, epsilon ijk for the third term? Because it says jik still.
I meant to write jik for the third term, because I switched I became j's and j became i's. That's what changing the dummy variables means.
so the key to this thing is that the order of the indexes in the epsilon has to be the same as the order of the derivatives in your...
No, because derivatives are commutative. That can be any order. But I'm just taking the way it was written and change the dummy variables.
So you could have an eijk d squared phi dxj.
Yeah, you could do it.
Fine.
Yeah.
I thought it's like,
Okay, I see.
But this is the way it was given, so I just stuck with that.
Okay.
So let's see. A is a scalar. So let's see. A is a scalar function. All right, gradient. So gradient A, right, is going to be, this is called gradient A, and you can look up what gradient means, steepest descent, etc. And what was the other one?
where little a is a vector?
Oh yeah, okay. The other one was if this is a vector, so if A is a function of x, y, z, then gradient A is going to be is going to be a tensor. So if we use an index notation, we can write like this: dxi, ei, aj, ej. So it's going to look like this: daj, dxi, ei, ej. So it's going to look like very similar to the. So this is a second order tensor. And this is it's basically a point-by-point gradient. Component-by-component gradient. Because basically you're looking at this component of j, and you're taking the gradient of each one. So it's very similar to the top term when we had the scalar, except each component you're doing their separate gradient. That's what you're doing. And this notes is included in the canvas. All right, did people do this one yet? A cross B dot A cross B is equal to A squared B squared minus A dot B squared. What I would suggest you do is I'll do the left side and I'll do the right side and make sure they match. You have to use one identity. The identity that you want to use for this is, well, the reason you get two terms is because basically, all right, let's just talk about this. So each of these, you're going to have epsilon I, j, k, a, j, b. I like my notation. Hold on for a second. Yeah, let me just do this over. So A, I, B, J, E, K, epsilon I, J, K. So you shouldn't have to look up anything to write this because this is what the definition of cross product means. That's the whole reason why we have this permutation symbol in the first place, right? This epsilon I, J, K just gives you plus and minus signs associated with if you have B cross A versus A cross B. All right. Now this is a good question. This is a good prep for the quiz. If I write that term, what should the subscript be on my next on this A? Good. Yeah. Do not make it I. If you make it I, bad things happen. I don't know what problem that is, but basically, even if you have the same variable twice, it's got to have a different index. A L B M E N epsilon L M N. Okay. So I would suggest you do it like that. You will have to use that theorem that we have at the very top, because you can see you got two epsilon. So the roadmap here, let me just tell you the sequence of steps. Well, the dot product is that's going to give you a delta Kn, right? So that's going to get rid of one of your things. And the other one, the other roadmap is you're going to have to use this to write in terms of the two deltas, right? And then you're going to get the basically two different terms. Okay, that's the idea. Do I need to say any more about that? Yeah? We have like 1 minute left. Yeah. Yeah.
Real quick, you got epsilon ijk dotted with epsilon lmn, but there are no indexes in common. So how do you use?
There will be, because that n is going to be replaced with a k.
Oh, right, because of the Dirac delta. Yeah. Okay.
All right. Now number 4. All right, class is pretty much over. But number 4, basically, if you got through all that, you should be able to do these problems. I'm not going to write it, but there's a couple. And I think by next class, if you can pretty much finish number 1 through 3, because we pretty much did them all together, and get through most of number 4, we can ask any remaining questions, and I can give you some help with the remaining ones. I need to give you a handout. Yeah, because we need to go through number 7 a little bit in class. I might have to give a handout for Reynolds Transport Theorem. Okay, now commences office hours. I've got a meeting at 11, but I'll stick around for about 15 minutes or so. We can do office hours here. On Wednesdays, there's a class immediately after this at 11, so office hours are in my office. But I'll stick around if you guys have questions or if you want to run through this.
Articles that are concerned, right?
Yeah, for the microfluidics. Yeah, you can send it by email, and I'll just give you thumbs up or thumbs down.
Okay.
Yeah.
There's
Yeah.
a few I have. I was waiting to see if anyone wanted to join me in the topic.
Yeah, I would. Yeah, just choose a. Yeah, it's only a 10 or 15-minute talk, so don't. So maybe choose 1 or 2. Yeah.
Yeah, that was my plan. Was just to choose one
Okay.
on the list.
Yeah. Do you know about microfluidics?
So I'm in Dr. Solchek's lab.
Oh, okay. Oh, great. Okay.
So it's my interest area.
Yeah. What year are you?
My second year PhD.
Oh, okay. Okay. So you're gonna take your quals?
Next spring.
Okay.
That's
Okay.
the plan.
Yeah. Oh.